कैमरा भी ऑन करना है. Hi, good afternoon, everyone. I think there is only one. The link जहाँ पे कुछ question है क्या नहीं? Okay, so I think only one person has joined, so maybe we'll just wait for a couple of minutes to start. Just wait for some more time. Yeah, so those who have already joined, if you have any questions, any confusion, you can just ask me directly here by in the chat box, or you can just ask me by switch on your microphone. I'll just make one clarification about the confusions. Good afternoon, Nishant, Abdul, and as well as Sikraf. So if you have any question, please type in the live chat box or please ask me. I just want to make one clarification, but that I'll do maybe after some time, because if some people more join, that will be better. I hope you are enjoying the course. Course is almost now in 6th week, so I think it's now in 7th week. So you have learned the basic part of the course. The theoretical part aspect is already done. Then the second part is more interesting, because in the second part, what we are going to teach is how you make your hardware design from C using HLS efficient, right? So in the sense, how do you take good decision about arrays, loops? What are the optimizations that tool have, and how to utilize them? So I try to cover that part as well as the other security part and other aspects. So the second part is more interesting in my opinion, and more practical concepts are has been covered, which is not covered in any textbook. So so I hope you'll enjoy second part more. The first part is mostly the theoretical aspects of the course, right? There is one question from Arman. What is the difference between hardware modeling using Verilog and C-based Verilog? So to clarify Arman question, so it is not C-based Verilog, right? C-based VLSI design, right? So the difference here is that when you write your code in hardware, so you need to understand exactly how much resource you need, right? How they will communicate, what will be used for what purposes, and what will be the latency of your design, what will be the how many registers you need, right? How many multiplexers you need. So you have to do everything from scratch, right? And then you then also you have to design for a big specification. It may run over time, right? Whether you have to make a pipeline design, whether you want to make a multi-cycle designs, right? So there are many aspects are there. And once you try to write your direct hardware modeling, that means you're writing your Verilog code directly. So it will take a lot of time to just come up with one design, right? And then say to develop almost takes 2 weeks to develop one Verilog for a specification that I've given, which is area efficient, right? And then I ask you to write a pipeline version of that. Again, you have to do it from scratch, right? So it's a lot of time-consuming process. So what this course is started, that can I develop this hardware directly from C code, right? You don't need to consider the hardware detail. What you have to do is you just write your code in C, use the tool high-level synthesis, that will automatically convert into RTL. So that's the best part of this course, that you to know the all detail of the hardware designs, or say how much, how to develop a pipeline designs or any other intricate part of the design, right, which is very time consuming. So even if you do not have an expertise in hardware modeling, say you are a engineer like me who has a computer science background, you want to develop hardware, then you write the code in C, use this tool that will give you the Verilog directly, right? So it's basically C-based VLSI design. And from this Verilog, you can use other tool like logic synthesis tool, physical synthesis tool to get your actual layout, right? Which will be built as a chip later. So it's kind of accelerate the process. That is why this hardware accelerator design. So you want to develop hardware from a specification, and then, but this is kind of very fast, right? So you make your whole design process faster, right? So that is the difference, that you don't need to write the Verilog, you have to write the C, and from there the tool will give you the Verilog, right? And another big advantage of this process is that, as I mentioned earlier, that if you want to develop a pipeline designs or you want to develop a fast design, which is basically very faster, right? So, or say you want to reduce the latency, you can have different design parameters. So those can be designed by just knowing certain pragmas or some optimizations that is available in the tool, right? Just enabling such optimizations, it automatically can generate a pipeline version of the design. You can develop a multi-cycle version of the designs and so on. Right? So that's the advantage of this process. I hope it clarifies Arman's questions. So yeah, Nishant looks a very sincere student. So yeah, I mean, and then yeah. So the second part is definitely interesting. I can assure you. Okay, so there is one question asked by Saurav. It is, can CS student do the fabrication process? So I mean, nowadays there are some work. There is a single work that I just went through last day, I think, even last Wednesday, is that even you can yeah, even you can ask. So even you don't need to become a Verilog or design engineer to develop a chip nowadays, right? You can write your code in C, the course that is talked about. So, and you use set of tools, right? That there are some tools which is commercial, which you have to pay money, right? For this HLS tool, it is the student version is free from Xilinx, the Vivado HLS that I use. There are open source tool like Bamboo that you can also use. But these commercial tools are kind of bit costlier in terms of license. But there are open source tools also nowadays. Like if you see, Google has developed one high-level synthesis tool called XLS. There are that open road tool flow was developed by Google, which is again do logic synthesis, physical synthesis, and you give you the layout, right? So to answer Saurabh questions, you don't need to know anything about hardware, or say have a very basic. I should define this way, that if you have a very basics of hardware knowledge, that is sufficient to develop a chip nowadays, because you just write your C code, you use high-level synthesis tool, you'll get the RTL, and then you use logic synthesis tool. If you think about from commercial, from Xilinx, it's IAC. If you go through for ASIC, if you use Synopsys design compiler, it will give you the gate level design, right? And from gate level design, you have to do this placement, routing, floor planning, all those things, and that is called physical synthesis tool. So there are tools available, right? So that will map everything to your layout level, and you will get the layout, and then if you know any vendor or any company that actually gives a fabricated chip, so you send your layout, they will give you the chip, right? And there are some company that give you chip in very low cost nowadays. I think $100 something, right? So it's easy. I mean, you can develop your chip very quickly with all the tools. So you just need to know how this tool works, what are the optimization it has, what is the impact of those optimizations, right? So then you can develop a chip from C code directly, right? And even the point I was trying to specify, that even nowadays there are a lot of tools. It's supporting that you write your machine learning, you have a trained model, right, which is in your TensorFlow or any other Python level code, right? And then there are tools that can convert them into C automatically, right? There are Keras to C kind of tools are there, open source. They will take your Python trained model and they'll give you a C code. And then you use this HLS tool, which will automatically give you the RTL, right? So now what does it indicate? That when you have a machine learning model, which if you run in a GPU, which is good, but if you want to run them in your processor or in your computer, it will be very slow. But what you are doing, you are effectively generating a hardware that will do you the training, right? So then you can map this particular hardware directly into FPGA, right? And then you can run your trading model in the FPGA board. So this is how you can actually bring your machine learning model into hardware, right? So you can accelerate this machine learning training, so testing process through hardware, right? So this is how people are working nowadays. Okay, I think it answer sort of questions. We have questions from Visual, I guess, Visual Narawan. He asks questions. I have watched till week 4. Will be writing code or implementing the hardware anytime in the course. So we'll not write direct Verilog code in this course, right? So what we'll do, we'll write C code, but we'll learn how to write good C code that will be automatically converted into hardware, right? So basically hardware efficient C code. So the next part of the course mostly will cover how do you write hardware efficient C code, right? So that's something we'll cover in the next part. Okay, I think it answered your questions, Vijpal Narayan. Then we have one more questions. Tech Matt, he's Matt here. Okay, so we have. I have watched till week 4. Will be writing. Oh, this is the same guy. Yes. Yeah, I think these are the same questions I have already answered. There is a question from Nishant. I have done PG diploma in VLSI, design and verification. How after designing a system in C, does it improve the latter part of the designing verification? If I understand your questions, see, the whole purpose is that you develop your chip in quick time, right? So you try to make your whole design process faster. As I mentioned at the start, that whenever you try to write your own Verilog, it takes time. Right? It's not easy to develop such Verilog quickly, right? So the advantage that if you use HLS or C-based VLSI design, you will write C code, which most of the time the C code is already available, right? And then you basically synthesize them into hardware quickly using the softwares, right? Synthesis tools. So the overall purpose is to make this whole design process faster. So because there is a concept called time to market, right? So in this there is everywhere there is competition, right? So there are maybe 2-3 companies try to develop certain things, and everybody wants to come their cheap first, fast in the market, right? So so everybody tried to finish this whole process as soon as possible, right? But there are so many things are there, as you mentioned, the verification. So important questions here it's not only synthesizing, right? You have to make sure that it does not violate any design rules. There are a lot of verifications. After every steps, you have to do equivalence checking, right? You have to do simulation. You have to make sure that your code that you get after, say, HLS or say after logic synthesis or physical synthesis, those are actually functionally correct, right? So you have verification part, and then you have also testing. To after the fabrication is done, you have to test your chip whether there is any stuck fault or any other kind of physical fault happen during the manufacturing process. So there are so many steps you have to cover. Then only you can bring your chip into the market, right? So everybody want to reduce this time, so they try to bring this chip as soon as possible into the market, right? And in this context, this C-based VLSI design is very useful. And as I mentioned at the introductory course, probably have already introductory video, that this HLS is extremely important in this context of hardware accelerator design, while you try to develop a specific chip for a particular application. You are not interested to develop a general purpose processor anymore, right? You try to develop a IP that will do one of the algorithm very fast, right? For example, you have a cryptographic IP, you can have a FFT, you can have a DSP IP. So all this is very application specific processor which can be developed very fast with HLS, right? So that's the kind of importance of this course in development of the hardware accelerator. Okay. We have questions from Manu Kumar Sharma. I write a C code after division and convert the code using a Xilinx XLS tool. Converted RTL was in terms of number of lines, or we can say the size is completely bigger than Verilog code. Yeah. So obviously Verilog code will be much larger as compared to the input C code, and the number of lines really doesn't matter, right? And why the number of line will be more? Because you're now describing the entire hardware. you have to tell how many components are there, how they are connected. So you have to develop you have to describe your data path interconnections. Then you have to describe your controller FSM, how many states are there, how they are connected. And then every state you have to describe what are the control value is going to the data path, right? So you have to describe everything. So the Verilog code is much larger as compared to the C code. But what it matters is that once you synthesize, it will give you some number. And there's the 3 parameter that is very important. What is the latency? The latency means how many time cycle it needs to give you the output, right? So latency is the first parameter. And then you have the clock speed, how fast your design can run, right? If it is running in 100 megahertz or 500 megahertz, people will try for a design which is running a faster clock so that you can complete the process quickly, right? And the third parameter is the area, how much area it covered, right? Is it too big, right? So these 3 parameters you have to play with. Either you try to reduce the area, or you try to reduce the time or clock speed, improve the clock speed, or you try to improve the latency, right? So these are the 3 parameters on which people works. So number of lines code does not really matter. What is important is that how efficient your Verilog code, right? Is it running in faster clock? Is it has less latency, or is it or it's consume less area, right? So these are the 3 parameters on which you will measure your code is good or bad. Okay. Manu has one more questions is can you please tell me how it's efficient in terms of resource utilization I'm doing in the FPGA? Yes. So this is what I just talked about. There are 3 parameters, not only the resource utilizations. Obviously, when you try to map into FPGA, the first target should be that whatever your design that must fit into the FPGA. So if you know FPGA a little bit, it has primarily 3 components, right? It has LUTs, lookup tables, which actually where you can map your combinational things, gates. You have DSP where you can actually put your multipliers, and you have RAMs, right, where you can put your array, large data. So when you buy a FPGA board, it has a fixed amount of hardware, right? The amount of money you will pay, you will get the size, right? So if you pay 30,000 or so, you will get a FPGA board which has probably some 30-40,000 of LUT, maybe some 80-90 DSPs, and then maybe some 10-12 RAMs, right? I'm just giving a rough number. But if you pay 3 lakhs, obviously you'll get a FPGA board that has much more resources, right? And now when you try to map your design to a particular FPGA board, it is a fixed number of resources, right? So you have to make sure that when you map, it must fit into the resource that is given in the FPGA board. If it is not, it will say that your FPGA board is small, right? It cannot fit into this FPGA board. Then there are 2 choices. Either you buy a larger FPGA board, or you try to optimize your design with various parameters like pipelining, and then say data flow optimization. There are many other optimization that we'll cover in the latter part of the course, with which you can reduce the design size, right? So it's basically you have, when you target the FPGA board, as long as it fits into the FPGA board, you're fine, right? If it is not fit into the FPGA board, then there is a problem. Okay. In this context of latency, I want to just clarify one thing. I think there are a few queries came from you people. So I just want to, I think there are some confusion in my video. I hope my screen is visible to everyone. Is the screen visible? Yes, right? I think so. There are a few more questions. I'll take up them. So yeah, what I want to just, yeah, visible. Thanks. So I think there is one confusion about the latency. So if you see this slide, once you take this behavior, this is the slide that I've used in one of the lecture for list scheduling. You see here, this is the DIFFQ example, right? And then say this is the one possible schedule. So for this design, the latency is 4, right? It is not 5 or 6. So if you remember that I have the way I've explained the sequence graph. So I always I remove all the inputs and I'll add a node or a source node, and then I'll add a sync node, right? So to calculate the latency, I'll just see how many time step is needed to execute my actual behavior, not the source node or sync node. So I think in one slide, probably by mistake, I somehow say the latency is 5, which is wrong. Please note that. So in some of the assignments, some of you are asking this question. So I'm sorry for that confusion, but it is clearly mentioned here the latency is 4, right? So it's basically the time 1 where operation 1, 2, and 10 is scheduling, time 1. Time 2, 3, 6, and 7 is executing. Time 3, 4, 7, and 8 are going to be executed, and time 4, 5, and 9, right? So the first 0 and n, these are the dummy operations. They are not actual operations, right? So when I show this schedule, you have to tell the latency is 4. It is not 5 or 6. If you take the schedule, that means here you can assume that time 0, no source node was there, and time 5, the sync node was there. But I don't consider them when I calculate the latency, right? So please be clear that the latency is 4 here. The time, number of time I need to execute my actual behavior, not the dummy nodes. Okay, so that's the only clarification I want to give you. I think this is clear. So I'll now take up the questions. There are a few questions here. One from Assam, Sigrap Masan. So she asked, I think this latency part is clear to everyone. If not, please you can put questions or doubts. So the question from Sigrap is, after modeling the desired hardware in C, you never develop the desired hardware in C, you will develop the software specification, converting into Verilog using the tool. Is there any way to see the designed hardware in a simulation environment? Simply put, can we simulate our own written hardware code and check it for functionality? Yes, so it is there, right? So once you write a C code, right, how do you simulate? It's just like your GCC, right? You write your C code, and then you basically you can just use your a.out, right? You compile and you get an a.out, and you run that a.out with different inputs. You'll get the output, and you know what is the correct output, right? So can I write something on the? Can I write something here? No. If I want to explain something here, you have to. This won't work here. Okay, that's fine. And then can I write here? Make it full stop. Yeah, so I'll explain how the whole process of simulation works here. Is my screen is not shared, right? Just give me a second. I'll explain the simulation process. Yeah. So suppose you have a function, right? You have a function which takes say A and B, and it produces say output C, right? So this is the function which you want to synthesize into hardware. So how do you simulate? You write your main code, right? Int main. In this, suppose you want to check for 1000 data, right? So you write a for loop, which is say I0, I less than 10,000, and then I plus plus, right? This function is doing something. I mean, I have not written the body of that function, right? So there are so many complex operations, say, and this module is say going to be synthesized into hardware. So this will give it into HLS, and it will give you the RTL, right? Which is very long, right? So what will you do? Simply you will read, says you can do scanf A and B, right? I'm not writing the contest. So I mean, if I write like this, you have to write percentage D, and then you write ampersand A, ampersand of B, right? So you'll get the value of A and B. Then you call function with these two values. You'll get C, right? So if C equal to expected output, right? So you know that in this function, if you give suppose this is doing A square plus B square, right? So suppose you are giving A equal to 2 and B equal to 2. So that means S square equal to 2 square plus 2 square, 4 plus 4, 8. So expected output will be 8, right? So you will just compare with the expected output. The expected output may be written in some file, right? So you'll just check whether the output that you obtain from the function that you have written and the expected output for this input are same or not, right? If not, then you say if it is same, it is not equal to, then say error, right? So you will just print error, right? So there are some bug. So you'll identify some bug in this function, right? So this process you will do. So this is the kind of simulation code you should write, that you have a function which is going to be synthesized into hardware. So what you effectively do, you will call this function iteratively for the number of input you want to run. So for example, I want to run for 10,000 cases. So every cases I will read the value. I can read from file, or I can give it from a scanf, and then I'll get call this function, and then I'll get this output from this function, and then I'll compare this output with actual output of what this value of AB, right? And if they matches, I'll say it's fine. If not, then I'll say there is some error. This is how you can do the simulation, and then you can just compile this code and run. Then you'll actually able to simulate and check whether this code is correct or not. Now, how do you check this Verilog is correct or not, right? So how do you check the Verilog is correct or not? So basically what will happen, this HLS, so whenever you synthesizing HLS, you have to give your test bench, right? So this is your test bench. Yeah, so this is your test bench, right? This is called test bench, right? Effectively, you're the testing code. And this is your actual function, right? So if you look into this way, you have, this is your actual function, and you have a main, which is calling this function every time. So this is what is your testing code, right? So if you compile this code and run, it will actually check whether this code is correct or not. So now when you, I hope some, all of you have already installed Vivoda HLS and try to synthesize some of the C code. What happened when you try to include the file, you have to say what are the, which function, what is the top level function you want to synthesize. You have to mention that this is my top level function. Okay, this fn. And this fn in term, they might call many other functions like fn1, fn2, any other functions. But you have to mention that what is the top level function I want to synthesize. Okay. And also you have to mention what is your test bench or test file. So you have to say this is my test file. So this may be tb.c, and this function is written there in say some other file, right? src.c. So you have to give this file as to synthesis, and you have to mention this fn as my top level function, and this is your test bench. So C simulation whenever you are, so in the this Vivoda HLS, in this Vivoda HLS, so within that there is a concept called C simulation. So if you click on C simulation, what will happen? It will basically run this code. And what will happen actually for 10,000 cases, it will just check whether your functions are correct or not. If there is something wrong, you it will just say that yeah, this is wrong, this is the problem, right? So the C simulation ensure that your C code is working correctly, right? Then you will do the HLS, right? HLS. So what this HLS does is it will convert this function into the Verilog, and also convert this test bench into also a test bench file, right? So it will also convert your C program that's this into a test bench in the RTL, right? So it will automatically done by the HLS tool. You don't have to do anything. Then there is a concept called RTL post simulation. You don't have to do anything. If you just write a test bench in C, and if you do HLS, automatically the test bench of C will be converted into corresponding test bench in the RTL, right? And then if you write RTL post simulation, if you run RTL post simulation inside Vivoda HLS, it will now check this Verilog code, right? So this Verilog code for this same set of input, right? So that means now if this passes, that means your Verilog code that is generated from the input C code, that is also correct, right? So you must write this this test bench for C, right? And then it will automatically convert into test bench for RTL, right? And then there are option if you and did all this, the Viva HLS also generate the test bench in model sim. It's a third party tool. Or inside the Viva HLS there is a RTL simulator, right? So it will just, if you click now RTL co-simulation, it will take the Verilog test bench and check your Verilog code in the similar way, right? So this is how you should check whether your C code is correct, and after RTL is generated, your RTL is correct. Hope this clears your idea. I mean, clears your doubts, right? I think, I hope this is clear. And then let me just go back and to see is there any other questions. Yeah. So so this was the question was asked by Sagrab. Yeah. And then there is other questions. Yes. There's one more question, sir. Also one question from Vishwal Narayan. I just want to give one suggestion. You must download one of the HLS tool, and specifically I'll suggest Vivado HLS, and keep trying to use it. And if you're facing any problem, you put questions in our discussion forum. We'll answer that. But just knowing the theory won't help you, right? In this kind of online course, see, I offer the same course here in IIT Guwahati. What I do, I give project, right? So what I do, I give project from different domain. I give project from image processing domain, cryptographic domain, machine learning domain. So I give some application. I ask them to synthesize them into hardware, and then you see whether you're able to do C simulation, HLS, and RTL co-simulation. Then I ask them to optimize it, right? You develop one RTL which is area optimized. You develop one more RTL which is latency optimized, or you develop one more design which is timing optimized, right? So this is the kind of project I give here. And that kind of project is not possible in this online mode. But I strongly recommend you all people you must download and try with the tool. Then you'll learn, right? You'll know what optimization doing what, right? What optimization impacting on area, which is optimizing impacting on the timing and so on, right? So this is very much important. Okay. So I think the Sagrab question was answered. Then Bijbal is saying that, sir, also one question regarding the three-stage pipeline lecture in lecture 11. Could you please explain what significance of three-stage pipeline if the delay is only 2? For example, in microprocessor, we learn it's a three-stage pipeline as fetch, decode, and execute. It is 3 clock cycle. I asked Google discussion also. Please reply appropriate. Yeah, I think it's good. I'll explain. I think that's the use of this discussion, right? I hope you are here, right, Visual? Yeah. So I'll just add on. Yeah. So I'll explain this pipelining concept in HLS. Do you have water here? Yeah. So what is pipelining? Suppose you have a design like this. Okay. Say suppose you have a design like this. Right. So suppose you have a design like this. This is the dependency, right? So you are giving say A, B, C, D, and you are producing the output out, right? So this is the, say I'm taking a very simple example, right? So here, let's say I just for this is plus and this is. Okay. So now, so there are 2 versions of the code I can generate from it. One is non-pipeline. Okay. In the non-pipeline version, thank you. In the non-pipeline version, what you'll do, suppose you create a schedule like this. Okay. So say suppose you create a schedule like this. So I'll just put it in this direction. So suppose this is the schedule you generate, right? So 3 steps, 1, 2, and 3, right? So this is the schedule you have generated, right? So this is 1, 2, 3, 4. So this is how we have generated. So now you see here, so you need 3 clock to get the output, right? So now if it is a non-pipeline one, you will give one input in say timestamp 1. Then it will take 1, 2, and 3. You'll give the next input in timestamp 3, right? Because sorry, in 4, 1, 2, and 3 it is done. Next input will give in 4, then it will take 4, 5, and 6. Next input will give in 7, and it will take 7, 8, and 9, and so on, right? So in every 1, 4, 7, 11, this fourth cycle, you're going to give new input, right? So this is what is the non-pipeline person. Okay. And what is the advantage of this? You can actually share resources here, right? So you can use as one multiplier, because at most one multiplication is happening here. So you can use one multiplier and one adder, right? So one mult, one adder to develop this design. So that means you're going to share this, right? So suppose this is A, this is B, this is C, and this is D, and this is E, F, G, right? So this is EFG. So what is going to happen? So you are going to use one multiplier for this. So you'll have a one multiplier, right? Suppose this is multiplier, and there is one more adder, right? So suppose this is your adder. So now you are going to multiplex the input A and E for this. Suppose, so the left input, right? So this is the left input and out input. So you have a multiplexer which will multiplex between A and E as the left input, and for the right input, it is basically B and F. So you have to give B and F, right? Then it will give the output, right? And this, it will go to either register E or G, right? So this will go to there, and there will be enable, right? It will say in the first clock this enable will be on, and in the next clock this enable will be on, right? Enable 1 and 2. So effectively, you see, you are able to develop the design with one multiplier and one error, right? That's the advantage of this design, right? So you are able to develop, and similarly, you can actually 0, 1, 0, 1, and similarly, there will be marks at the input of this multiplier adder, right? Here you will give C, and there will be one more input, say something is coming, say, right? So suppose this is only coming here, right? So suppose this is basically E, right? This is the same E basically. This is F. Sorry, this is E, this is F. This is C. Right, so that means here you will, this is E only coming here, say this is E only, the same E is coming here, right? So if I draw it correctly, the same E is coming here, which is possible, right? So that means you are going to multiplex between C and E. You will give C and E here, C and E, and here you will give G and D, right? D and G. And there will be a select line here, right? So if you give 0, so in the first clock you're going to do A plus B, right? So you'll give 0 here, so A will come here. You'll give 0 here, so B will come here, automatically A star B will happen. In the next clock, you'll give 1 here, so E will come here. You'll give 1 here, F will come here. As a result, E into F will happen, right? So the same multiplier is conducting both A into E and B into F. This is how the resource sharing happens, right? And this will go to either F or out, right? So this is how the design. So this design, every fourth clock your new input will come, but advantage is that your resource is very less. You have only one multiplier and one adder, right? Now let me see the pipeline version. Okay, so what I'll do, so again my schedule is this, right? So this is my pipeline version I'm discussing now. Pipeline design. In the pipeline design, I'll make the schedule like this. Okay, so what will happen now? I need, so this is my pipeline design. put a register here. So I'll put a register here to store this value. I'll put a register to store this value. I'll put a register here to store this value. I'll put a register here to register, right? And I'm going to use 2 multiplier, no sharing, right? 2 multiplier, 2 add. So I'll have 1 multiplier, 2 multiplier, 1 add, 2 add, right? So I'll just give exactly this design, okay? Then what I'll do, in the first clock, I'll give, say, in the first clock, I'll give ABCD, right? So suppose I've given the value, say, A1, B1, C1, D1, right? So say A1 equals, say, 5. So what will happen in the first clock? So this part is not doing anything, right? Because this part is still the pipeline is not full. So what will happen in the first clock? It will just do A1 into B1, and it will store here A1 into B1 in this register, A1 into B1, and this will store C1 plus D1 in the next clock itself. So next clock will come in the next clock itself. Second clock, say I'm giving A2, B2, C2, and D2. Okay, so then what will happen? Because this multiplied input is now A star B and C1 D1, so it will do this multiplication and store the result here, right? It will store A star B into C plus D, right? C1 D. So A1 B1, C1 D1. So this part, so that means this is now working on the first set of data. So this is stage 1, stage 2, and stage 3. So stage 2 working on the first set of data, and this what will do? Now this is input A2, B2, C2, A2, B2, C2, and D2. So this will create A2 into B2. This will create. So it will create A2 into, and this will create C2. Sorry, and this will create C2. Sorry. And this will create C2 plus D2, right? So I think you understand the basic concept, right? So what is happening here? And then in the next clock, so suppose we have given A3, B3, C3, and D3. This is in third clock, right? So you are giving first clock, I'll just write this way. So this is your clock 1, this is clock 2, this is clock 3, right? So every clock you're giving next set of input. And then what will happen in the third clock? So this adder now will take this and this C2, so they'll be registered to store here. This will be registered to store here also. So this will store C1 and D1, and this will store C2 and D2, right? So in the third clock, so third stage of the pipeline will now work on this plus this. So it will create A1 into B1. Yeah, so A1 into B1 start C1 plus D1. So actual calculation plus C1 plus D1. Where there is one more plus C1 plus D1, right? So you'll get the so third stage now working on the first set of data. You are getting the actual output corresponding to A1, B1, C1, D1. So this now will work on the data corresponding to A2, B2, C2, D2, right? So it will have A2 plus B2 here, and that will A2 into B2, that will multiply it with C2 plus D2. And that data will be stored here, right? And the first stage will work on the third set of data. It will now work on A3, B3, right? So it will create A3 plus B3. Here it will create C3 plus D3, right? So now in the next clock, we'll give C4, D4, A4, B4, C4 and D4, sorry, C4. So now in fourth clock, you'll give this data. And then what will happen? So after third clock, your output, first output is ready. In the next clock, your second output will come, right? And next clock, your third output will come, right? So first output will come after 3 clock. So this is your output 1. And then every clock, so this is clock 1, clock 2, clock 3, and so on. So 1 will come here, O2 will come here, O3 will come here, O4 will come here, right? And you're giving input, first input here, second input here, third input here, fourth input here, and so on. So once the pipeline, the advantage is that because if there are 3 stages, the question asks is three stages. There are 3 stages, but all stages will work on a different set of inputs, right? And advantage here is that in every clock, so you will get the first output after third clock, but after that in every clock you're getting output, right? Every clock you're getting output. Whereas here, so if there are say n data, right? So if there are n data, n set of inputs are there, what will happen? First output will have to come in 3 o'clock, and then for rest of the input every clock, right? So you'll get overall latencies 3 plus n minus 1. Right? Here, how much time it will take? So it take 3 clock, right? So 3 into n, right? So this is the advantage. So this is much faster. This is effectively n minus 2, right? If there are n set of input, it will take only n plus 2 number of clock to give you the complete the whole execution, whereas it will take 3n, right? So this is what is the difference between a pipeline implementation versus non-pipeline implementation. So to summarize, non-pipe implementation use less resource, right? Here I have used 1 multiplier and 1 adder. Here I am using 2 multiplier, 2 adder, because there is no resource sharing. But non-pipeline version, this is what is called latency, and this is the called the throughput. Throughput is low, right? Every third clock you're going to get the output, whereas here in every clock you're going to get the output, right? So it will be much faster, right? So if you want to create a much so you want to complete or execute the things much faster way, so you should create a pipeline design, right? And if you want to reduce your area, you should go for non-pipeline design. So there is a trade-off, right? But I hope your concept of this pipeline and non-pipeline is clear with this example. Okay. Okay. So I think Vishbal and questions was answered here. Is there any other questions? Otherwise, so 2 suggestions from my side. First thing is that do practice. You take certain projects, you try to do yourself, and you try to, this is the first thing, you should be used to with this tool. And second thing is that you try to apply various optimizations of the tool and try to see how pipeline. So all this schematic is actually available, right? If you open this, there is an option. If you install Xilinx ISE, it will give you the schematic, but the diagram, right? So you can actually see the difference. The way I draw the diagram, exactly you'll see the similar diagram when you create a pipeline and non-pipeline version of this design, right? You'll see this is the structure is coming, where it will be structure like this will come for non-pipeline. And you should understand what is the trade-off between this, right? Then only you'll be able to utilize this tool properly. Okay. Yeah, thank you, everyone. If there is no further questions in a couple of minutes, I'll close down. So yeah, there is one question. Yeah, thank you. Yeah, thank you, Vishbal. I hope I am able to clear your doubt about the pipeline implementation. It is similar to the way this processor works, but only it create a different data path, so that it create multiple stage in the design, and it actually works. Different stage works on the different set of data. Right? That's the kind of trade-off or the advantage of the pipeline design. Yeah, thank you everyone who joins online and also have interest in my course. I'll be very happy to answer any questions you ask here, or any questions you have during any lectures. You put the question in the discussion forum. I have a very experienced TA. They will answer. If they could not, I will answer. So, but I want to make this course useful for you, right? I mean, all possible way I want to make this course useful for you. Okay, I hope all questions are done. Thank you, everyone, for joining here. I will have 2 more live sessions. I hope you will join again and ask all the doubts you have in the course. Thank you.